All right, welcome to week 11, RC circuits. In this, we're going to apply Ohm's law with our resistor and current relationship, as well as our relationship between capacitance charge and voltage. And we're going to use both of those to figure out our time in terms of charging and discharging a capacitor. Okay, so we're taking what we learned last week with a capacitor, as well as what we observed relatively in terms of the charging and discharging times, and now we're going to put a bunch of equations to it. Okay, so good and bad news. Good news is we're going to see how differential equations can be applied. However, we're not actually going to need to use them on a regular basis. So what happens is we use these differential equations. We're going to integrate a differential equation in order to derive our charging and discharging equations. However, once we know those charging and discharging equations, we don't have to keep using integrals of those in order to find these, okay? But it's a really cool practical application of some of that higher level math that you are learning in your calculus classes, all right? Just as a reminder, we've been using our total voltage throughout the semester. I like to use VTotal. However, we're going to start to use, and it was in with Kirchhoff's laws as well. This E is the electromotive force. It is meaning the total voltage. So that is coming directly from your power supply, whether it is a battery or whatever power supply that you have. Okay. Also, as a reminder, your voltage is your joules per coulomb. Okay. So this is our RC circuit in a nutshell. We're going to put a resistor in series with a capacitor. This is the original circuit. So this is how you would build this if we were building this in reality, where this is a switch. Okay, you did this in the simulation this past week when you were getting the intro to capacitor, when you're getting to know those. Okay, so if we move this, if we close that switch, we are charging our capacitor. The second this switch closes, our current starts to flow, and our current can be determined by our Ohm's law. Okay, remember the capacitor does not affect the current, but the resistor and the total voltage does. And so in order to find, that is going to be our maximum current, is when that switch first closes, and that's going to be your total voltage or your EMF divided by the resistor in the circuit. Okay. As this circuit goes, okay, this capacitor is going to charge up, so it's going to be gaining charge on the capacitor, which means our current is going to decrease. You hopefully saw that as that light bulb dimmed. We used the light bulb as a resistor so we could visually see that it was on, and then it was slowly decreasing, and then it was off. Okay, so that's what we're going to determine. So how long does it take to fully charge, as well as what's happening to that current as it is charging. So the current is going to decrease as the charge over the capacitor increases. So the maximum current can be found using Ohm's law for when that switch is first closed. So once it hit, this has reached its max, so our Q max here is over that capacitor. And that Q max has to do with our electromotive force and the capacitor that you put into the circuit. All right, so now if we go back to what the original one looks like, and we take our switch, we disconnect it from the battery, and we connect it to this other side here, we get the discharging. So essentially we're taking the battery out of the circuit. So now we just have the resistor and the capacitor. So the capacitor is going to discharge. It acts as our power source or our voltage source. So the current is going to go in the opposite direction through the resistor and continue around and eventually die off again. So that discharge, once again, right as soon as we click that switch over to discharge, we're still going to have our maximum is going to be based on our total charge divided by our resistance. Now remember, if we started with a 12 volt battery, then our capacitor is going to charge to a maximum of 12 volts as well. Okay, so the battery tells us what our maximum voltage is. Okay, so that's our E max. Our Ohm's law is going to tell us what our current maximum is, and then our capacitance equation is going to tell us what our maximum charge is. So that is when it is depending on what's happening in the circuit. Okay, so those maximums are important to remember, that we get those using Ohm's law or capacitance equation or just looking at our battery. Okay. Alrighty, so this is what we know. Okay, we know current is equal to our voltage divided by resistance, so that's going to give us our I max. Okay, our capacitor equation is going to give us our Q max because we set the capacitance and we set the voltage. We need to remember that our current is our change in charge divided by our change in time. So that's where our time aspect is going to come in here. And we also know our loop rule, right? And so that's from our Kirchhoff's law. We're putting this all together here, where if you go around in the loop, the total voltage should add up to 0. What we need to know is how to calculate the current, charge, and voltage as the capacitor charges or discharges. So that's where this timing aspect is going to come in, is how long does it take to charge and what is happening to that current or charge as it's going. We're going to learn about the time constant for each individual circuit and how that is applied. And we're going to learn all equations. So we're going to get probably like 6 to 8 equations today. So be prepared to organize them. And I would make sure that they are labeled as as charging or discharging equations. We are going to use Euler's number, which is E. Okay, and remember, we're not going to necessarily need to know what E means because we're going to derive it into our capacitor or our charging and discharging equations, and then we're going to use that to solve. Okay, and so it should be a button on your calculator if you need to find it. It should be a capital E, or sorry, a lowercase e. It is approximately equal to this here, but again, if it's in your calculator, it's kind of like pi, it's a known number. So you can find it on your calculator. And remember that when we're isolating things, the opposite of E, so if something's multiplied, the opposite is dividing. So when we have an E, we're going to take the natural log in order to isolate whatever the exponent is. Okay? Okay, so back to our capacitance or RC circuit here. So we've got our maximum voltage, we've got our resistor, and we've got our capacitor. When the switch is closed, the capacitor will begin to charge. Okay, as soon as the switch closes, we can find our I max by our V max divided by our resistance. Okay, once this is fully charged, we can find our Q max by knowing our capacitance times our maximum voltage. All right, so those are how we get our maximum totals. All right, and that is for when we are charging. Okay, so what's happening here? This does not charge in a linear fashion. Okay, it is an exponential function. So as it charges, okay, this is our 0 point here, and then this is our max. So this would be E. V cap is referring to V on the capacitor. So at any point in time, the voltage across the capacitor is increasing. And once again, it's increasing exponentially. Okay. So our current, however, remember we said as soon as this connects, as soon as that current starts to flow, that is when we are at our maximum current. And as you saw, that light bulb dim over time as our charges were gathering on the capacitor. As our charge of the capacitor is increasing, the current going through that resistor is decreasing. All right, and once again, it is decreasing exponentially. So our maximum comes from our maximum voltage divided by our resistance. And then at any point in time, we can find the current through the resistor based on this exponential function. So what we're going to look at now is this time constant. So a time constant in an RC circuit is the time it takes to charge or discharge. And this time constant is found by multiplying the resistance in ohms multiplied by the capacitance in farads. It has a Greek letter of tau, which I call a fancy T, and our units are in seconds, okay? And so our time constant is going to tell us it's the time required to charge to 63%, or it's the time to discharge to 37%. And we're going to look at that in just a minute here. Okay, so we'll put a little pin in that. But our time constant is equal to RC. I have this on another slide with all equations, but that is what our time constant is. And so you can see on this graph down here, okay, that after we go to one time constant, our voltage is increased to 63% across the capacitor. Okay, after two time constants, it is 86 and so on and so on. Okay, and we are getting this 63% by doing 1 minus e to the -1 for one time constant, -2 for two time constants, and so on. So e to the -1, that's where we end up with our, 37%, okay, or a 0.37, and so it's actually 1 minus, and I'm going to show you that here in a minute. But that's where these numbers are coming from, okay? So going back to this, after one time constant, and we can find our time constant by multiplying our resistance by capacitance. So after one time constant, our voltage across the capacitor is going to increase by 63% of the total voltage. So again, if our V max is 12 volts, then our voltage after one time constant would be 12 times 0.63 in order to get that voltage. Okay, so the opposite is happening with our current. We start with our maximum current as soon as that starts to charge, and that's the current going through the resistor, right? Because it builds up on that capacitor. So we start at our maximum and then we're decreasing. So after one time constant, again, that's e to the -1, we get 0.37 or 37% of our total maximum current, okay? So I mentioned these are a little repetitive. It is really important to see these multiple different times until it clicks. Once it clicks, you're good to go. But sometimes it takes watching a few different videos from a few different sources as well as reading in order for this to click. All right. So the time constant is the time it takes for the capacitor to reach 63% of the EMF value during charging, or 37% during just charging. So these graphs I took from your textbook. As I just mentioned, it is really important for you guys to read that textbook. It goes into a little bit more detail, and it's just written in a little different way. The more different sources you can use to get a broader understanding of this, the better. All right. So our charging, this is our charge of the capacitor versus our current through the capacitor, okay? So our charge is increasing, and the same thing's gonna happen to our charge that happens to our voltage on the capacitor. So the opposites are happening, right? Our voltage is increasing on the capacitor as it is decreasing through the resistor. Once we first start to charge it, it's acting like a steady state or a regular circuit, but over time, that voltage is dropping because the charge is being built up on the capacitor and our voltage across the capacitor is increasing. Okay, so you can see here after one time constant what is happening to this charge, and the same thing is happening to the voltage. We're increasing by one time constant each time. So the first time constant is 63%. So what's happening to the current is also what is happening to the voltage across the resistor. We don't often worry about the voltage across the resistor. We're more looking at it on the capacitor. However, for your information, this is what's happening, is that on the on the resistor, we're starting as soon as the circuit is starting to charge. We start with our maximum voltage across the resistor, and it is dropping on each one here. After one time constant, we have lost 37% of the total voltage. All right, so these numbers, why are they the way they are? Well, we're gonna look at that in just a second. Here's another version of the same graph that we can see what's going on. Okay, so again, it's gonna be really important to read your axes to make sure we know what we're looking at here in order to read these properly. All right, so these are our equations. Now I'm going to attempt to show you these, how they get there. Okay, so first of all, if we look at our loop rule, right? So if we've got a battery, we've got a resistor, and we've got a capacitor. All right, so our loop rule is going to be V across our resistor minus V across our capacitor is equal to 0. All right, so our total is going to be, this is IR, this is Q over C is equal to 0. Now, we've got I's and Q's. We don't like to deal with I's and Q's, but we know that our I is actually our change in Q over change in time. And I'm going to be consistent with my little q here is equal to 0. Okay, so now we're going to isolate this here. All right, and so to do that, we're going to end up with, oh dear, I just lost all that work. Okay, that's okay. So we were here. I'm going to change the order I write. Okay, so from there, we're going to isolate and we're going to do R dq over dt is equal to E minus Q over C. Okay, but we still want to isolate that. So we're going to divide both sides by R. In order to put this into one format here, I'm going to end up with dq over dt. I'm going to add this C here in order to C minus Q over R C. Okay, so in order to extend this, in order to put this together, I had to multiply this by C, right? So if we do this, we're doing the same thing to the top and bottom, and now they're both C, which I can put here, and then I can divide both sides by R, right, to get rid of that, and then I have R here and an R here. So then we just put this all together like that, okay? So from there, we're going to integrate this differential equation. Please take a look at your textbook in order to go through all of this from one step to the next. Also, I posted a Khan Academy video where the gentleman goes through it nice and detailed on how you actually get to there. Okay, in the sake of time, we're going to go ahead and jump from one to the next, which is to get, to get to these, oh my goodness, there we go, to get to these equations here, okay? So again, see derivations in textbook. What we're doing here now is we've got our voltage over our capacitor is equal to our total voltage. The equation is actually coming from this charge here. So when you integrate those, you end up here where this is actually C over that, or C times that, which is also your Q max, okay? So anytime we're asking a question, if you know if it's asking this and you don't know your total charge, remember you can use those maximum equations or original equations that we've used the last couple of weeks in order to determine the maximums, okay? Okay, so notice this could also be written, our V capacitor is our total maximum capacitance, 1 minus e to the negative t over tau. Okay, that RC is tau, so if you know tau, you can multiply that beforehand or not. Some of your expert TA questions are going to actually have you find tau and then plug it in, but just so you know, it can be written either way. All right, and this 1 minus this is how we get that 63%. Okay, because if your time is equal to your time constant, that is just going to be e to the negative 1. And so that's where those previous 63 and 37% are coming from. All right, so this is charging a capacitor. Your voltage across the capacitor increases with time, and that is the equation. Your charge follows the same curve, and this is how we determine how the charge is increasing over time. And this time is related to the time constant tau, which is your current, sorry, not your current, your resistance times your capacitance. So here's your capacitor. equations. Notice that current is not in here because current does the same thing whether it is charging or discharging. It starts at its maximum and then it decreases to 0. Okay, so discharging a capacitor, we're doing things a little bit different. All right, discharging graph for the capacitor is the same as that of the resistor. There will be a time delay due to the time constant of the circuit. So we're starting at the maximum V over the capacitor and going to 0 as it discharges. So this opposite is, instead of 1 minus E, we're just having E to the negative time over tau. Okay. So this is for discharging. We start with our maximum charge, right? Our capacitor is fully charged and it's decreasing exponentially. Again, this curve, we're going from our maximum. At every point in time, we can figure out what the current, not current, but current meaning is in time, the exact or the instantaneous, I guess is a better word to use, the instantaneous current or charge, oh my goodness, sorry, is at any point in time. Okay, and we can see our time constants here again based upon that resistance and capacitance of the circuit. So the voltage across the capacitor is following the same curve as the charge over the capacitor, where the voltage over the resistor is also doing this as well, because once again, we're starting at that maximum current and then we are decreasing that current as the charge discharges. All right, so here is the capacitor voltage where we're starting at that maximum and going to 0. The current, again, is also going to 0 here, the way that this is written. It's just upside down. Okay, so our discharging function, all right, and this one here, once again, we are looking at once we connect this switch, we disconnect it from the battery, and so now our voltage source is coming from this capacitor. So as soon as we connect the circuit, that current is going to flow in the opposite direction, which is why that graph was inverse. It's going in a negative direction this time, and it's going through that resistor until it depletes the charge over the capacitor. Okay. So here is our calc going through here when we are finding our voltage at any point in time is going to be our maximum voltage multiplied by E to the negative T over RC. Once again, we could write that as our voltage at any point in time, or it could be over the capacitor, is equal to our maximum E to the negative T over tau. Or you can just write in RC. It depends on what information you have. If you're given tau, just write in tau. If you're asked to find tau first, then use tau instead of RC over again. So this current equation is true for both charging and discharging, right? Because the maximum current is going to happen as soon as it starts to charge or as soon as it starts to discharge. That is when the maximum current is going through that resistor. The charge is going to follow the same the same graph as the voltage when we're looking at discharging. So once again, your charge at any given point in time, and that's the charge on the capacitor, is equal to the maximum capacitance that we found from the original maximum equations, and that's multiplied by E to the negative T over RC or negative T over tau. Okay. And again, after a time constant RC, so that means that your time is equal to tau, which would make this -1 or -2 and so on. So again, here's if an isolated charged capacitor is connected across a resistor, it discharges at this rate. Okay. This is from Hyperphysics. I love Hyperphysics. Hyperphysics is not good for learning in the first place because it kind of like this I took from it. It tells you everything at once, but it is an awesome place to review. Okay, so please use I like to use Hyperphysics. You've probably seen some of their graphics in some of my presentations. So Hyperphysics is a great way for reviewing. It's showing you here that, oh gosh, sorry. Our VB or V max is equal to, your voltage drop across the resistor and capacitance. As your voltage on the resistor is decreasing, your voltage on the capacitor is increasing. And then it gives you some nice little indication. So at time 0, we have no charge, no voltage across the capacitor, but all of our current has to do with our total voltage divided by resistance. And then as time reaches infinity, our charge is going to be from the capacitance and total voltage. Our capacitor voltage is equal to that total voltage, and then we get 0 current. Okay, and it's showing these equations here. Instead of using Q max or I max, it's actually inserting these equations here. Again, these are all tools that you should have in your toolbox or your equation sheet in order to solve these problems. So we may not always have Q max, but we know we can solve for Q max by using our C and V max, okay? So again, these graphics coming from Hyperphysics, a great spot to, and they've got all of the different subjects that we've learned over the semester. It's a nice little review spot, okay? So this is the current. This is the current in both situations. Again, your current maximum happens as soon as it starts to charge or it starts to discharge. All right, and so these here are your equations for discharging. The only difference is that this is your Q max and then this is your I max. However you want to write those down is up to you. Sometimes you're going to use both formats, or you can calculate one and then plug it into the other. Okay. All right. Same graph that we already looked at. Again, very repetitive. This should be charging. This is charging current. Anyways, charging current and the charge on the capacitor. So really the big difference is this one for charging and that is not there for discharging. Here we go. So this is how I would set up your equations, where you have both discharge and charging kind of in a nice format, so you can look at them both. Once again, your charging, you have this 1 minus E versus that is not present when we do our discharging. Note that our current for both cases is the same because it acts the same way. It's just going in the opposite direction for charging and discharging. So this is our charging, our volts versus our amps. The lab that I'm going to demonstrate and then you guys are going to do is we're going to actually look at some of these graphs in real time. But this is what they look like. Once again, very repetitive. Sorry. Okay, so this is where the fun part starts. Okay. I will kind of walk you through this verbally, and then I want you to try these on your own. So you should be calculating these on some paper or a whiteboard or whatever you have to make sure you know how to do these and use these as a checkpoint before you start your expert TA. Okay, so here we have an RC circuit. The capacitor is initially uncharged. These are important words to make note of. When the switch is closed at time 0, how much charge is stored on the capacitor at time 0.85 seconds? Okay, so we have some very important information here. We know our maximum voltage and we know our resistance and we know our capacitance. Okay, so how much charge is stored at that time? So we know that we are charging. Okay, so our Q at any point in time over the capacitor is going to be our Q max multiplied by 1 e to the negative t over RC, or you can put tau on there. We haven't calculated tau yet, but maybe we will, so we can determine that. Okay, so our Q over time is our maximum. Remember, we can use our maximum current, sorry, not current, but voltage multiplied by our capacitor. Okay, 1 minus negative, and this was going to be 0.85 seconds. And that is divided by our resistance, which was 220 ohms. And this, I don't want to go back, but I want to say it was 4.2 milli, which is 10 to the negative 3. I apologize if that's wrong. If I go out of this, I'm going to lose all this work. Okay, so, and then we can include, sorry, this capacitance should also be here as well as our total max voltage. And so now we're just properly putting this, that's a weird looking cue, properly putting this all into our calculator to solve that equation. Okay, yes, it was 4.2 millifarads, which are 18 volts. And so once we put all of that into our equation, we are going to get that our charge after 0.85 seconds is going to be 0.455 coulombs. Okay, I'm missing a decimal place right there. So how much current is running through the circuit at time 0.85? Wow, my decimal places got funny on this version, sorry. Okay, so that's where we're going to use our current at any point in time is going to be our current maximum times e to the negative t over tau, or RC. All right, but we're not sure what the maximum current is, but again, your maximum current is going to be your total voltage, which is 18 volts, divided by our 220 resistor. So that's going to be 18 volts divided by our 220. And so you can either plug 18 over 220 into this equation and solve it all at once. I recommend using some parentheses when you do that, or you can solve them individually. It's however you like to use your calculator. Okay, so our I max is going there, our time and our C is going there. And again, you should, oh, sorry, I thought that was a different slide. In this case, you'll end up with 0.0326 amps. Okay, so this right here, initially uncharged or starts to charge or is charged and going to discharge, is going to be very important words to be highlighting or making note of when you're reading a question. Okay.